All right, so to finish out the videos for lesson 5, let's recap what we talked about in the previous lesson. We talked about finding the rate of change at a particular instant of time. And what we did is we used secant lines to help us determine that. What we found was that by calculating or finding the slopes of secant lines as we moved the point closer to the point, in this case at x equals 2, what ultimately happened is that the secant line ultimately became a tangent line, since the points, as you got closer and closer to this point, got so close that it was hard to distinguish between 2 points that we took, that it appears to be a tangent line. Okay, so and in terms of a rate of change, what we did is we took the slope as the rate of change. We took that value as the rate of change at that point. So you would think, talking in terms of a tangent to a curve, such as if I drew just a curve and I put a point here at the curve, we'll say that that's at x equals a. You can give it a number if you want. But you would think that we would define the rate at which the value of the function y equals f of x, here's a function y equals f of x, is changing with respect to x at any particular value of x, let's say x equals a, to be the slope of the tangent to the curve at x equals a. Okay, but the problem with this, with thinking in terms of average rate of change, remember, is if we use just that single point, then when we find the slope, m equals, then I've got f of a minus the f of a, all divided by a minus a. If we use the average rate of change or the slope formula for a point at a point itself, you're going to end up with 0 over 0, which is what we talked about previously. So the question is, how do we find the slope of a tangent line without 2 points? Well, let's go back and revisit average rate of change. The average rate of change for a function in the interval x to x plus h. Now remember, x is an x value, x plus h is some greater x value. We would evaluate the function at the greater of the two x's, which would be x plus h. We would subtract f of x, and we would divide that by x plus h minus x, and that would all clean up to be f of x plus h minus f of x over h. So average rate of change can also, remember, represent m, which is slope, and it would be calculated as f of x plus h minus f of x over h. When we're talking about an instantaneous rate of change, we're still going to use the slope formula. See how these two match? Well, these two match. But since we want the instantaneous rate of change, the slope at a point, then we're going to apply limits. We're still going to use the slope formula, f of x plus h minus f of x over h, but now we're going to put the limit as h approaches 0. Do you remember where h approaches 0 comes from? When did we see that? Well, we saw that when we were looking at the rock and the fruit fly population problem. Remember when we said that the slopes of the secant lines, as the slopes of the secant lines decrease, the values of x are decreasing, which means h is decreasing also. and h is the difference between any two x values. So from 2 to 2.1, remember we said h was 0.1. From 2 to 2.01, the h value is 0.01. And then the h value between 2 and 2.001 was 0.001. So your h values are getting smaller and smaller and smaller, therefore approaching h as h approaches 0. So the h's are approaching 0. So that's where this limit comes into play. You want to evaluate the function. You want to find the instantaneous rate of change by finding the limit of the slope formula as h approaches 0. And whatever that turns out to be will be the slope of the tangent line at a particular point. Okay? All right, so let's go ahead and use this example. We have y equals x squared. Let's find the point on the curve at 2, 4. So let's say that this is 2. The point on the graph is 2, 4. And there is a tangent line at the point 2, 4. So what I want to write the equation for this tangent line to the parabola at this point. So we need to think, what things do we need to write the equation for a line? You need two things. A y-intercept would be great, but it doesn't have to be a y-intercept. It can be simply a point. So we need a point, and we need the slope. So we have our point 2, 4, okay? Now we need to find the slope. And so here's what we need to do. We need to just find another point. What would the x value of that point be? This would be 2 plus h. And even though I have physically kind of separated them, 2 plus h is going to represent 2 point something very, very close to 2. Okay, but we'll call that 2 plus h. Then if this is 2 plus h, what would the y value of that point be? Well, how do I find it? How did I find 4 when x was 2? Well, we substituted 2 into x, squared it, and got 4. So your y value here for this point will be whatever 2 plus h squared is. Okay, so how do I find the slope of this tangent line? Since I want the slope of the tangent line, then I'm going to use the limit as h approaches 0 of f of x plus h would be 2 plus h minus f of 2 divided by 2 plus h minus 2. So why is this 2? Well, this 2 represents an x value, and our x value was 2. So now it's a matter of substituting 2 plus h in for x. So I still have to carry my limit of 2 plus h squared minus 2 squared. I substituted 2 plus h in for x and squared it. I substituted 2 in for x and squared it. And now all of that's going to be divided by h, because the 2's cancel, as h approaches 0. Okay, I'm going to clean this up mathematically. The limit as h approaches 0, this is 4 plus 4h plus h squared minus 4 all over h and my 4's here will cancel, and I'm left with the limit as h approaches 0. Notice between these two there is an h that's common, and I can reduce that to 4 plus h. So now I have taken an expression that if I had substituted 0 here and here, we would have ended up with 0 over 0. So, and the same thing here, I would have ended up with 0 over 0. So what I did was we rewrote this, we kind of manipulated this algebraically. I've got this now in a different form, and now to find the limit, all I have to do is substitute 0, and that gives me 4 plus 0 equals 4. So there's the slope. Here's my point, and I can write the equation in point-slope form. So I have y minus 4 equals the slope, 4 times x minus 2. And there is your equation. Y minus 4 equals 4 times x minus 2. And so when you're asked to find the equation of the tangent line at a particular point, all you just have to know, you have to figure out what the point is, and you have to determine the slope. And the slope is going to be determined using limits. Okay, so to define the slope of a curve at a point, you have to have a function, you have to have a point, a comma f of a, and the slope of that function at that particular point will be exactly what we just said. You are going to find the limit of the slope formula as h approaches 0, and of course we have to say provided the limit exists. All right, so let's look at an example. Let's look at a different example. So let's say you're given a function f of x equals 1 over x. First thing I want us to do is to think about what does that graph look like? Well, just very basic. This is the reciprocal function. So if you recall, we have a graph that looks like this and this. So we want to find the slope of this curve at any point we will call A on the graph. So this is going to be a very generic slope. A could represent that point right there. It could represent this point right here. So if I want to find the slope of the curve at x equals A, then I know that I have to calculate, I can calculate the limit of f of a plus h minus f of a divided by a, well, and I don't even have to have a plus h. I know what it's going to simplify to. It's going to simplify, it's going to simplify to h. So over h as h approaches 0. So this is your slope formula, and this turns out to be h because in the slope formula here, you lose your, in the slope formula here, you will always lose those x's. In this case, you would lose your a's. Okay, so now what I need is I'm going to substitute a plus h in for x. So the limit as h approaches 0 of 1 over a plus h minus, I'm going to evaluate the function f at a, so that'd be 1 over a, all divided by h. All right, so I've got some cleaning up to do because if I substitute 0 here, if I substitute 0 here, that gives me 1 over a minus 1 over a, which is 0, over 0, so I have to do more work to be able to find the limit. So, going back up here, I need to find common denominator. There's my limit as h approaches 0 My common denominator is going to be an a times a plus h. This numerator becomes a. I will subtract, in parentheses, a plus h, and all of that's going to be divided by h. All right, so now it's just a cleanup process. My numerator, I'm distributing or subtracting both a plus h. So I'm going to lose my a's, and I'm going to have a negative h over a times a plus h. And this h here is over 1. So I'm going to, instead of dividing, I'm going to now multiply by the reciprocal of h, which is 1 over h. And what happens there is you get your h's there will cancel, and this should give us something now that we can substitute 0 for. So h is approaching 0. I have a negative 1 in the numerator. I have a times a plus h. And now when I substitute 0 for h, I get negative 1 over a times a, which is a squared. So this is an expression for finding the slope of this curve at any point x equals a. Okay, so that looks like a weird slope since no numbers are involved. Well, now let's just say that, what if we wanted to find the slope at, let's say this point, and let's say that point has a value of 2. So if this is 2, at x equals 2, which that's your a value, then I can find the slope, m equals negative 1 over 2 squared, which is negative 1/4. So estimate, and I'm sorry that this is small, but does this seem reasonable that the slope of that tangent line would be negative? Yes, and a fraction less than 1. It does, because this slope is very flat, or this line is very flat. Okay, what if I wanted to find the slope at the point x equals, I don't know, negative, I'll mix it up a little bit. What if I wanted to find the slope where x is negative 1/2? Okay, so now I'm looking at the point perhaps like right here. So I would simply take my negative 1/2 and I would plug it in for a and square it, and we get negative 1 on top. When you square negative 1/2, you get positive 1/4, and when you change the division to multiplication, you end up with negative 4. And that line, that little tangent line, is steep, and it's falling, which makes sense that it would be a negative because it's falling, and 4 because it is steep. So I took the function and we applied the instantaneous rate of change formula to finding the slope of this function at any point on the curve. And so when we have something very generic like this, we can use this slope to find the slope of tangent lines at any point on the curve. Okay, so now I'm going to, let's go to the next page. And we're still continuing with the function 1 over x. So I'll put this back up here. F of x equals 1 over x. Let's see. So find the slope of a tangent line at the point x equals 3, and then write the equation. So let me put this back up here as well. So our function is 1 over x, and our slope is, what was our slope? -1 over a squared, which a is just another way of describing x. So, to find if we want the slope of the tangent line, I'm going to take my expression for slope, -1 over my x value for a is 3 squared, so my slope is -1/9. So to write the equation for this line, this tangent line, I need a point. Well, I have the x value of the point. How do I find the y value of the point? Well, take your 3 and substitute it for x in the original function, and we get 1/3. So I have my point, I have my slope, and now I have enough to write my equation. Y minus 1/3 equals the slope, which is -1/9 times x minus 3. So why don't we take a look at this? Let's take a look at this and see what it's going to look like graphically. And I may have said this before. I apologize for this. This is a reflection of the tiles on the ceiling. So I'm going to go in, well, turn it on first, clear that out, and I will go to y equals, clear out what I have, and I'm going to type in the function 1 divided by x. And then I'm going to actually type in the tangent line. I'm going to type it in as negative parentheses 1 divided by 9, close the parentheses, open parentheses, x minus 3, close the 3, and then I have to add the 1/3 over, so plus 1 divided by 3. So here I have the function 1 over x, and here is the equation for the tangent line. And now I'm going to do a zoom 6, and you'll notice in blue is the function, and you'll notice in red is the tangent line. And this is a little crowded, but if I press trace, my x value is 3, and if I push 3, there's the point, 0, or not 0, but 3, 1/3, and there's the tangent line. So if I were to go in and change my window a little bit, I'll change my x's, so from 0 to 10, and I change my y values from, I don't know, -1 to 1. Let's see what that looks like. It may not be a good one. Yeah, it is. Here you can see the tangent line a little bit better. And so here's your tangent line. And here's x equals 3. I'll trace, type in 3, and enter. So there's the point, and there's your tangent line. All right, so finding the slope of a function at a point must involve the limit of the slope formula as h approaches 0. All right, so let's look at this from a slightly different perspective. Here we've got, where does the slope equal -1/4? Okay, so what does -1/4 equal? That equals the slope. So m equals -1/4. Well, what was our formula for slope? -1 over a squared. So I take -1 over a squared, set it equal to -1/4. The negatives will cancel each other out, and if I cross multiply, I can get a squared equals 4, so a equals plus or minus 2. So what does that look like? This is what it's going to look like, and I'll just draw it. So we know we had this graph, or branch, we know we had this kind of branch. So at x equals plus or minus 2, so let's say that this is 2 at that point, and -2 this point, then, of course, my drawings look terrible. then the slopes of these these two tangent lines is -1/4. Okay? So, finding the slope of a tangent line is going to involve your slope, finding the limit as h approaches 0 of the slope formula. Let's take a look at one more example to kind of put it in perspective. And let's go back to like another rock problem. It says an object dropped from rest to fall freely near the surface of the earth will fall y = 16t squared in the first t seconds. Okay, we've seen this before. Find the speed of the falling rock at t = 1. Well, remember, speed is a rate of change, a rock, okay? So if I want to find the speed of the rock at t = 1, then I'm going to use a limit formula, and I'm using the limit of the function evaluated at 1 plus h minus the function evaluated at 1, all divided by h as h approaches 0. So here's the formula, here's the definition of instantaneous rate of change. So we want to find the speed of the rock at t = 1. So I'm going to go in and substitute 1 plus h into t. So that's the limit as h approaches 0 of 16 times 1 plus h squared minus 16 times 1 squared all over h. And that is the limit as h approaches 0. This will be 16 times 1 plus 2h plus h squared minus 16 all over h. And then distributing, I get 16 plus 32h plus 16 h squared minus 16 all over h. And look, anybody know what I left off? The limit as h approaches 0. Can't tell you how important it is to carry your limit with you. Okay, so then what I'm left with, an h will cancel. I'm left with the limit as h approaches 0 of 32 plus 16h. Now I can substitute 0 for h, and I get 32. So the speed, or we'll say at t = 1, the speed of the object is 32 feet per second. And so that is how we can find the speed of an object at a particular instant of time. Okay, so one more thing I would, something really to think about, and I don't know where this word came from, but when we talk about a normal to a curve, we're talking about a line that is perpendicular to the tangent line. So normal means perpendicular. So if you're asked to write the equation for the normal line, or the normal to the curve, f of x equals 4 minus x squared at x = 1, visually, this is what you're looking for. Let's say we have a quadratic, opens down, so we kind of have something that looks like this. Yeah. And we want to find at x = 1, we want to write the equation for a tangent line. Okay, let me rephrase that. We want to write the equation for the normal to the curve. So what I've drawn is the tangent line. This is a tangent line we want to write the equation for the normal line, which is the line that is perpendicular. So this would be normal. Well, all we have to do is find the slope of the tangent line, because if we know the slope of the tangent line, we can determine the slope of the normal line. How do we find the slope of the tangent line? Well, we're going to use that limit of the function evaluated at 1 plus h minus f of 1 divided by h as h approaches 0, and substituting 1 plus h into the function. Now it's going to get a little bit little messier, but that's okay. We have 4 minus 1 plus h squared, and I have to subtract the function evaluated at 1. So there's 4 minus 1 squared, all divided by h. All right, so cleaning this up, I got some algebra to do. So the limit as h approaches 0, I have to square this and subtract it. So I'm going to have 4, I'm going to try to do this in a different color, minus 1, that would be 2h, so minus 2h, that would be h squared, so that's minus h squared. And then I have minus 3. And all of that is over h. So now we have the limit. Notice that we have 4 minus 1 is 3. 3 and the negative 3 will cancel. Have an h that will cancel out of those. So what I have is the limit of negative 2 minus h as h approaches 0. That's just, this is what all of that cleans up to be. So I can substitute 0 for h, and so the equation for the normal line, this is the slope of the tangent line, is equal to negative 2. So the slope of the normal perpendicular will be positive 1/2. Remember, perpendicular lines have opposite reciprocal slopes. So if I want to write the equation for the tangent line, then my equation will be, do I have my y value? No. So take 1, here's my slope. My point is going to be 1 comma 1 squared 3. So my equation, y minus 3 equals 1/2 times x minus 1. I know that got a little bit squeezed in there, but there's your equation. All right, so just as a reminder, when you want to find an average rate of change, you're just finding straight up slope. So it would be, you would evaluate f of b minus f of a over b minus a. But if you are wanting to find an instantaneous rate of change, you're going to find the limit of a slope formula as h approaches 0. And so those are the two things: average rate of change, instantaneous rate of change, and how they are different. Okay, so I'm going to stop there, and we will maybe look at these two examples in class.